Hello out there. Uh, Today's lesson is going to be about one specific kind of discrete probability distribution function. In previous lessons, we were discussing probability distribution functions, and there's one kind that emerges quite commonly, and it's anytime you have two possible outcomes. Something happens or it doesn't happen. So if you can arrange a probability situation where something happens or doesn't happen, then you have a binomial probability situation. Now, if you compound that with total number of trials, that is the number of times you're going to see if something happens or doesn't happen, that's how you can create a distribution function as a function of the number of trials that we take. For starters, just to get grounded on this, we want to look at binomial probabilities. We're going to start with a type of dice, die, I guess, that has 4 black sides and 2 red. My skills at the time I made this graphic, this is kind of old. Obviously, I wasn't good enough to draw a proper cube that had 4 black faces and 2 reds. So you're going to have to use your imagination. However, 4 black faces and 2 red, and I want to figure out how many different ways can there be 4 blacks, how many different ways can there be 1 red and 3 blacks, or 2 of each, or 3 reds and 1 black, or 4 reds. So recall from earlier counting chapters on combinatorics and so forth, we can see that there's only one way to get 4 blacks. You roll a black the first time, second, and third, and fourth. Now, to get 3 blacks, you can roll a red the first time, the second time, the third time, or the fourth time, and then all the rest would be black, which means there's 4 different ways that that could happen. And then you can see, by following the similar pattern, we can see that there's this combinatoric and Pascal's triangle row happening right down here. So this is 1, 4, 6, 4, 1, which is the 4th row of the Pythagorean. Yeah, because this is 4, dummy. Anyway, moving on. So we understand then that not only if we wanted to say, for example, what's the probability in 4 rolls of getting 2 reds and 2 blacks, we have to appreciate the fact that that could happen in 6 different ways. And then we have to consider the probability of each of these different ways. And so there's a way to generalize that, and we'll observe that in a minute here. Let's take a look. Excuse me. Now, let's just start with some notations. We're going to let B be the event of rolling a black, and then R is going to be not B, which is the event of rolling red. So the probability B is 2/3 because there's 4 black faces out of 6, which reduces to 2/3 probability. And then the converse then to not be black or to be red is a 1/3 probability. So the probability of getting 4 blacks is probability of black and black and black and black. It's a 2/3 probability, 2/3 probability. So basically you're taking a 2/3 4 consecutive times. And of course, there's going to be 1/3. The probability of getting a red is going to happen 0 times. So here again, we can see how beneficial 0 power equaling 1 is. If that was 0, then we would screw up our probabilities. Anyway, there's only one way for that to happen. Remember on the previous slide, we saw that there's only one way to roll 4 blacks. And so we're going to call that 4 choose 4. And if you put it all together, the actual probability of getting 4 blacks in a row is going to be 4 choose 4 times 2/3 happening 4 times, and a 1/3 probability never happening. So to extend that then, what about the probability of getting 3 blacks and 1 red? So the probability of getting black and black and black and red. Consider again that we have 3 different chances to get a black, which is 3 2/3 probabilities, and then there's a 1/3 chance of getting a red. But again, from that earlier slide, we know that there's 4 choose 3 ways in which there will be 3 blacks. So we have to multiply these outcomes because essentially it's 2/3, 2/3, 2/3, 1/3 is one of the ways it could happen, but it could be 2/3, 1/3, 2/3, 2/3. So the order can change, and we have to account for that, and that's what the combinatoric is doing for us. So the probability of getting 3 black and 1 red is going to be the 4 choose 3, 2/3 probability happening 3 times, and the 1/3 probability happening once. We can generalize that. Take the same dice, and we're going to roll it 30 times now. And I want to say, what's the probability of rolling 10 blacks? We can deduce from what we just saw previously that we have 30 trials. I want 10 of those outcomes to be black. 2/3 probability of having a black to the 10th power, that's 10 different times it happens, and then the 1/3 probability is going to be to the 20th power, so that's basically 10 of them are going to be black and the other 20 are going to be red. And again, there's 30 choose 10 different ways for that to happen. So this is going to be a large number, but of course these are going to be very small numbers. We could probably expect a relatively low probability. So this is essentially a function. It's a probability generator, and so there's some the way that it's notated, and I'm going to show you some more of this later. Is we have probability the event occurs times the probability that an event doesn't occur, and then n choose x times. That's basically what all of this notation is saying, and that's the general form for a binomial probability distribution. So, using some cheesy, corny example of an archer that has a 90% chance of hitting the target with each arrow. If 5 arrows are fired, determine the probability generator and hence the chance of hitting the target. Twice only, at most 3 times, or at least once. This is a great opportunity to review some of that language, at most and at least. The simplest one is twice only. So he's shooting 5 arrows, but he's only going to shoot or hit 2 of the times, given that he has a 90% chance of hitting. You expect a pretty small number. So we have 5, choose 2 hits, 9/10 probability of those 2 hits landing, and then a 1/10 probability of those 3 hits not landing. Gives you this very small number. Dude's going to hit more than twice, you can be sure of it. At most 3 times, which means basically he can hit the target 3 times, 2 times, 1 time, or not at all. The most he can hit it is 3 times. So one of the ways we can do that is to simply add up from our probability distribution generator, no hits, 1 hit, 2 hits, and 3 hits, just by saying 5 choose 0, 0 times 5 times, 5 choose 1, 1 time 4 times, and so forth. So we put all of this together and we can calculate the probability of no more than 3 hits, which is slightly greater chance because there's more different ways to get no more than 3 hits. At least once, whenever you see at least, you might think sometimes it's easier to subtract from 1, and that's no different here. At least 1 hit is easily more easily stated as 100% chance minus the probability of not hitting the target at all. So that means he's going to have he's going to hit 5 times or 4 times or 3 times or twice or once, and that's all covering at least 1 hit. So we just take away the probability of not hitting it at all from all the other chances, and we're in. So simply do 1, subtract 5, choose 0. 9/10's never going to happen. 1/10's going to happen 5 times, and you get, well, yeah, he's going to get at least 1 hit. It looks like almost 100% chance, 90% chance accuracy, shooting 5 arrows, that at least 1 time he's going to hit the target. So it's important to make sense of this work while you plug and chug through the formulas. That's why I'm pointing that out. Just real quickly, because the video is getting long, if we have just looking at just another really quick example, a fair coin tossed 8 times, the probability of attaining exactly 4 heads. With coin tosses, it's great because it's always going to be a half probability of success, half probability of failure. But that only accounts for 4 heads and 4 tails, but there's 8 choose 4 ways of that happening. In other words, there's 70 different ways that we can get 4 heads and 4 tails. Therefore, we multiply 70 by our 1/256, and that the probability works. So you can kind of, I can see from here, you can get the hang of this. But in the next video, I'm going to talk a little bit more about expected value and variance, because with binomial probability distributions, there's a really elegant outcome there. So stay tuned for part 2 of this short series. Thank you.